like to get an estimate of x given y. I really want more, by the way. I mean, you know, you've got to know that just knowing the conditional mean is very little information. Just like knowing the mean of a random variable is very little information, right? I mean, in Gainesville, we get the mean forecast for tomorrow, and we're never told the variance is infinite. You know? It's just, but this is, like I joked about how probabilists are brave. This is an incredible optimal control problem. I mean, optimization problem. You're looking at the argmin of the L2 distance between z and x, such that z is some function of y and is in L2. All right. So this puts in two constraints on g. You know, g of y has to be measurable with respect to the probability space we're looking at, and it's got to have a second moment. That's just awesome. And wasn't the homework cool? Were the solutions uploaded? I don't know. Or maybe not. Was this homework 1 or 2? Or I had you do both? Oh, damn, you haven't seen it yet. But hopefully we were successful. When you looked at a quadratic estimator, you got a really close fit. So anyway, so there's this, which we've done. You should have done it before. I don't want to say linear, I want to say affine because it's there's a constant offset. So okay, so these could be vector-valued random variables. And when I say affine, I just mean that's a linear function. That's an affine function. We have a constant thrown in. Right? And you all know how to do this. Now, the thing is that we want to do is we want to find out how to think about this, how to get efficient algorithms and recursive algorithms and things like that. And I'll just remind you of one trick you typically do to condition your data to make it easy to solve. We don't know what these numbers are at first, but if we rewrite this in a different way, we do. Makes it easier. So this is the most trivial way of sort of modifying your data. Normalize everything so it has a zero mean. Okay, and in this case, what's C0? And so I had A's here. I have different numbers here because I've changed my coordinates. Instead of the Y's, I'm looking at the Y tildes. All right. So you know, optimizing over the A's or optimizing over the C's is the same thing, right? Because there's a one-to-one mapping between the two. So what's C0, everybody? You know, when I do this minimization? Well, remember x minus x hat times y, well, so I'll say tilde I equals 0 for all I. And also x minus x hat dotted with 1 equals 0. I have to have my errors orthogonal to my data. All right. And what does it say to say that x minus x hat dot 1 equals 0, it means I take that random variable, multiply it by 1, and take the expectation. So this is just the expectation of that times that, which is the covariance between x and yi, right? And that's just the mean. So because of the fact that the error is orthogonal to any constant random variable, we know that this is 0, which means that C0 all right, so this makes things easy, and mainly, I mean, more than anything, it makes it easy because the notation fits so nicely. We have these equations here. Immediately we got C0. We also get a bunch of equations to get the CIs, because we just go through and we multiply by error equations and we're done. I mean, let's derive the optimal estimator in 10 seconds. Might as well do it. This is review, but it's good review. So we've got, let's plug this in. Oh, wait. Hey, everybody. Look what you made me do. You made me make a mistake. I forgot the covariance of x hat and y tilde I. All right, there's a difference there. I left out a term. How many of you did? Come on. Keep your eyes open. All right. So if we rewrite these equations, what do we get? We get the dot product of x and y, normalized. And just plug it in. So it's all right, now I didn't make a mistake here. I know that I've got, when I talk about covariances, everything's always centered, right? So I'm taking x hat, I'm subtracting off its mean. I'm taking yi, I'm subtracting off its mean. I mean, it doesn't look like I subtracted off the mean here because I had an x hat, not an x hat minus its mean. But the y tilde has the mean subtracted. So adding a constant x hat doesn't change a thing, all right? Yep.
Would that be y 10?
Say it again?
Should it be covariance of x hat over yi?
No, because that's what I was just saying. Covariance means that. So the covariance of z and w means the expectation of z tilde times the expectation of w tilde transpose, if they're matrices. All right. And so, so it's, I could put in the tildes if you like, but yeah. So if I was talking about, yeah. All right, so that's true. So you're absolutely right. Let's write it down as an expectation. And so that looks like a matrix vector product, right? This is just equal to the covariance of y. That's the covariance matrix of the vector y times c but evaluated I. You know? So here I did 2 steps from here to here. I know that the covariance is just the expectation of that times that with a tilde thrown in, and I took the sum outside, right? All right, cool. So there you get it. So we're done, right? We can put this in one giant picture, and we have that the covariance of x, will that be a row vector? So these are, I'm assuming these guys are scalar right now. So the covariance of x, yi is the same as the covariance of yix. Given this definition, if everything's scalar, doesn't matter. Because I want to write this in the right way. From all this, if I write it in matrix notation, I get the covariance of y times the vector c, no i's anymore, is this, this vector. And that's how you get this famous formula. First, c is equal to the inverse. And the way you're used to seeing this is right here, that x hat equals the mean, and I'll write it like this. It's C transpose Y tilde, written in matrix form, vector form. And the reason I was fussing with this is I was thinking I'm going to have a column vector for C, so I take its transform, I get the right thing. And so the transpose of this, I write in reverse order. And this ended up getting flipped around. So that's the famous formula that you can memorize. You've got a y tilde. First, you condition it through this matrix inverse, somehow normalize it in some nice way. And then this covariance is like a mapping from the y world to the x world. That's how you memorize this formula. Okay? A conditioning step, and then a mapping step, and that's it. All right. So anyway, that's like, step 0 of the Kalman filter. But it's a monster, because this, if you've got more and more data coming in, after a week, this is a 10 million dimensions high, and I've got to invert a 10 million by 10 million dimensional vector. You don't want that. You don't want that. So we want to be able to do this recursively, and that's what the Kalman filter is. So I guess that's it for today, I think, unless there was something else, because I can't imagine going further. Yeah. So I think we'll blow off most of it on Thursday. I mean, basically, again, like I said before, this is like the dumbest thing you can do, although it does lead to a beautiful formula. All right. Innovations is a very brilliant thing to do, but we could just do it now if we wanted to. Well, you're doing the homework. It's Gram-Schmidt. All right, let's blow it off. So you can blame Caleb here. All right, so I have data coming in, and most of it's redundant. All right, I mean, basically, the yi's are noisy measurements of some state. The state's not moving very quickly. The difference between y, n and yn minus 1 is not that different, and that's why, in fact, because of that, in a lot of applications, this matrix will be very close to singular because your data is so redundant. And so what you do Thank you so much for telling me to do this now. It'd be crazy to wait until Friday. I think most of you have probably seen this before, maybe? I don't know. So given my data, I'd like to widen it. And how would I do that? Well, I've already told you I want to do it in a recursive way. I'm going to have this data coming, n is going to be time. And so, in zero mean. And we could assume that the y tildes were, the y's were tildes already, but we don't need to do that. What's I1? If I say I want to do this in a recursive way, I don't know anything else but y1. And there's a hint here, I want it to be zero mean and not throw away any data. I'm just going to take it to be y1 minus its mean, yes. And how about I2? Well, I've got the new data that came in, but I want to subtract off what's redundant, all right? And so you just do that. So it's just a slight refinement of what we did before. Just a little comment. So in this literature, you typically put in a hat, which means you look at the best linear estimator, right? And that's going to make everything uncorrelated. So we are going to do that. But if we actually were able to compute the conditional expectations, then we're going to find that these innovations is a martingale difference sequence instead of which is way more than uncorrelated, right? And then you just keep doing this. What's I3? It's just the new stuff, And we know the geometry. We basically we have this space here. Like, just take a look at this case. We have here the Yep. Yep. When we do this, when we, for example, in this this wide sense conditional expectation, we're looking at three-dimensional subspace of random variables. So linear combinations of the data, y1, y2, and constants, because we're always looking at these affine predictors, not linear predictors, they're affine. We throw in constants. And we have our new data that came in, which we visualize as a vector, y3. And all we're doing is we're projecting. And then basically it's a simple matter to see that just like here I wasn't throwing any information, The same notation I used here. Right.
Or in the plane, your projection plane, what's y3?
Well, no, yeah, so y3 hat is well, the wide sense conditional expectation of y3 given the data. So I'm just recalling what I mean by this, all right? You know, so when I'm talking about a conditional expectation, this wide sense, the second, when I'm talking about a conditional expectation, this wide sense setting, I'm looking at the projection on a finite dimensional space, and it's just the space the linear space generated by the random variables I put in here, and you slap in a constants as well, all right?
So y3 has the best, or it's a shorthand notation for the best linear estimator?
The best, yeah, y3 has, I was right, yep, it's the best linear estimator. And this, and there's the error, and I3 is the error which we know is orthogonal to this data. So, you know, by the orthogonality principle, I3 is orthogonal to anything in this space. In particular, it's orthogonal to y1, y2, and constants, and it's also orthogonal to the other innovations terms because they're living in this space as well, all right? So we know it's uncorrelated. And we don't lose anything. So all these steps are invertible. You know? So given all the i's, I can unfold this and get the, well, that's not quite true, actually. I almost said something false. I said I can invert these steps. So given the innovations, what's missing? Can I reconstruct the y's or not? Thank you. Let's think about so you know, to be seen. So given the expectation of y1 and so basically, I'm not losing information. You know, so and this is just a scalar anyway, so it doesn't matter. You know, it's just a constant. Yep.
Is that artificial gas?
What's that?
Is that artificial gas?
No. This is just reality. So if somebody, I assume I have a model where I know the mean of y1. By the way, that's an issue to remember. Throughout this, we're assuming we know a lot about the problem. Like, it's a race now, but we assumed we knew the covariance matrix. Okay, that requires a model. You know. But so given that, we know that this is equal to the mean of x plus some, what was it again, covariance of x comma I times the covariance of I inverse. I wish I wasn't using I looks like a identity matrix, times I. And they're uncorrelated and zero mean, so we're okay there. All right. And that's what's pretty here is what's this? This is just a diagonal matrix. So I said that I is the covariance. The covariance of I, because I say it's uncorrelated, the covariance is just the diagonal matrix with variances. That's right, like that. And so this is, so the, how do we say this? X hat k is the expectation of xk. And then, oh, actually, that just scales. Well, hold on a second, I'm making a mistake here. Oh, that's right. Does that look right to you? No, it's a K. I'm sorry, there's no K here. I got myself confused. It's a sum. Excuse me. I just got myself totally confused. That's the trouble. Yeah, hold on a second. This is, be quiet everyone. There's a sum here, that's why I'm getting confused. All right. Where it's been erased now. The covariance of x and I is nothing more than the expectation of x times I transpose. I got confused because I lost my planet. All right, I'm back here. When you take the covariance, you take the random vector times its transpose. And so this whole thing is a sum, because that's a row vector, that's a scaled identity matrix, and then that's a column vector. And so what I meant to do is put a sum of a k here. And this has a lot of meaning to it. You notice it's sort of recursive, right? Do you see it? It's already recursive. If I want to go from n to n plus 1, all I do is I add another term. All right. So there you have it. You know, basically that's the useful thing. The fact that the covariance is diagonal is what makes it all work. All right. So it's very pretty. I mean, geometrically, that orthogonality means you're taking out what the new information is. But more important is algorithmically, that is a recursive algorithm, right? Because you're taking a running sum. As you get the next term, you just add a term. Okay. And so these, something is going to be going to 0. Because this is turning into an infinite sum. So these covariances must be going to 0. So something's going to disappear. Cool. So thank you. I'm doing this adaptively because I'm just trying to, there's so many things to do, but I will send an email to you all in the next 24 hours and give you a heads up on what's to come on Thursday, and it'll be fun, I promise. None of these long calculations.